Imagine humanity finally reaching the stars, building colonies on the Moon, Mars, or even the icy moons of Jupiter like Europa. It's the dream, right? But there's a massive invisible problem waiting for us. Low gravity. On a world like Europa, where gravity is just a tiny fraction of Earth's, our bodies would wither away. Our muscles would atrophy, and our bones would become brittle. The common sci-fi solution is a giant spinning habitat to create artificial gravity. But what if you need to go outside? What if you're stuck on the surface for weeks? The moment you leave that spinning ring, your body starts to waste away again. It's a huge limitation. But what if the solution wasn't a massive stationary structure? What if the solution was something you could wear? What if the very suit that keeps you alive could also solve the gravity problem? Let's explore a concept called suit loading. Instead of building giant centrifuges, we could use the exoskeleton itself to simulate Earth's gravity, no matter where you are. The principle is simple. On a moon with weak gravity, there isn't enough force pulling you down. So the suit adds that missing force back in. It's like a personalized gravity generator. Think of it like this. To feel like you're on Earth, the suit needs to constantly provide a downward force that makes up the difference between the Moon's weak pull and Earth's familiar 1 gram. But just making the suit heavy isn't the answer. That only works if the local gravity is already pretty strong. No, this has to be smarter. The exoskeleton would use advanced actuators or magnetic resistance systems in its joints. With every step you take, every object you lift, the suit would actively resist your movement, forcing your muscles and bones to work just as hard as they would on Earth. By adjusting this resistance, we could perfectly tailor the gravity for each person. An astronaut in peak physical condition could have a full 1 gram workout with every step, while someone recovering from an injury could have the resistance lowered for rehabilitation. This turns the entire surface of a new world into your personal gym, constantly keeping you strong and healthy. This wearable gravity system has some incredible advantages over a spinning habitat. First, mobility. You're not confined to a single spinning structure to stay healthy. You have the freedom to explore the entire lunar surface, conduct research miles from your base, and live in non-spinning structures, all while your body gets the workout it needs. Second, customization. A spinning habitat has 1 gravity level set by its size and rotation speed. That's it. But a weighted exoskeleton can be tuned in real time. We can adjust the force for different tasks or for different individuals' health needs. And most importantly, the benefit is immediate. From the moment you put the suit on and take your first step, your body is counteracting bone and muscle loss. There's no downtime, no period of low gravity exposure when you travel. The suit is always on, always protecting you. Of course, there's a huge challenge: power. A suit that's constantly pushing and pulling against you 24/7 would need an immense amount of energy. Today's batteries just wouldn't cut it. But what if the suit didn't just consume power? What if it could also generate it? This brings us to a truly elegant idea. What if we combine the concept of suit loading with the principles of an electric motor? Instead of just draining a battery to create resistance, the suit could use magnetic fields to do the work and generate energy at the same time. Here is how it would work. The suit itself would act like the moving part of a motor, the rotor with powerful magnets and conductive coils embedded in its joints and boots. The floor of the habitat, or even the ground plates laid out on a moon base, would act as the stationary part, the stator generating a complementary magnetic field. As the astronaut moves, the magnets in their suit move through the magnetic field in the floor. This interaction creates electromagnetic resistance, a force that pushes back against the movement. This resistance is our simulated gravity. The suit's computer would control the field strength, ensuring the astronaut feels the exact force of 1 gram. But here's the genius part. This entire process is based on the principle of regenerative braking, just like in an electric car. When you create magnetic resistance, you are essentially converting kinetic energy, the energy of movement, into electrical energy. Every step the astronaut takes, every jump, every lift, induces an electric current in the coils. This is the flux you generate. That harvested electricity can be fed right back into the suit's batteries, or even into the colony as main power grid. So, the harder the astronaut works, the healthier they get, and the more power they produce for the colony. It creates a perfect symbiotic loop where staying healthy literally helps keep the lights on. This turns a biological necessity exercise into a valuable resource, making the colony more self-sufficient and resilient. It's an incredibly efficient, brilliant solution. Now, you might be thinking, this sounds great for a moon base, but what about a space station in zero gravity? And won't all those magnetic fields fry our brains? Those are excellent questions. And the answer is that this system is not only viable for a space station, it might be even more practical there. And no, it would be designed to be completely safe. In the total weightlessness of space, the need for artificial gravity is absolute. Astronauts currently spend hours every day on bulky resistance machines just to slow down bone and muscle loss. This magnetic exoskeleton would provide that resistance constantly with every movement, integrating health maintenance seamlessly into their daily lives. And a space station is a closed, controlled environment, making it even easier to install the magnetic stator components into the floors and walls. Any power generated would immediately help run the station's life support systems. As for safety, the concern about magnetic fields is valid, but this system would be engineered to be harmless. The magnetic fields would be localized and controlled, only active where the suit's joints or boots interact with the floor. We're not talking about a giant, room-filling magnetic field. The fields used would be low frequency, unlike the high-frequency radiation that causes cellular damage. Our bodies are already accustomed to Earth's magnetic field, and we routinely and safely experience much stronger fields during medical procedures like MR is. A well-engineered suit would direct the forces precisely where needed, keeping the astronaut's body and their brain well below any safety threshold. It's not wishful thinking. It's the next logical step in crewed spaceflight technology. So, how do we combine all these ideas into one incredible piece of technology? The key is a layered design. You can't just wrap an astronaut in magnets and hope for the best. The suit has to perform multiple functions: protect from the vacuum of space, shield from radiation, and provide simulated gravity. So, let's build it from the inside out. The innermost layer of the suit, right against the astronaut's body, would be the life support system and a protective Faraday cage. This would be a fine mesh of conductive material, like copper, woven into the fabric. Its one and only job is to block dangerous external radiation, like the high-energy particles you'd find near Jupiter. This is the astronaut's personal radiation shield, keeping them safe from the harsh environment of space. It's a purely defensive layer. Then you have the outer layer of the suit. This is the active, interactive part. Embedded in the outer shell, especially around the joints and in the soles of the boots, would be the magnetic components, the coils and powerful electromagnets. This is the system that interacts with the magnetic field in the habitat floor. This is the layer that does the work. As the astronaut moves, this outer layer creates the resistance that simulates gravity and simultaneously generates electricity. Separating these two layers is crucial. The inner Faraday cage protects the astronaut from outside radiation without interfering with the magnetic system on the outside. And the outer, mechanical layer can be made robust and even replaceable, since it's doing all the physical work. This layered approach creates a suit that is safe, efficient, and incredibly capable. It's a perfect fusion of protection and performance. So let's put it all together. What we've designed is more than just a spacesuit. It's a personal habitat. It creates a safe, pressurized bubble of air to breathe. Its inner lining acts as a Faraday cage, shielding the astronaut from deadly cosmic radiation. And its revolutionary outer layer uses magnetic interaction to force the body to work as if it were on Earth, maintaining muscle and bone density. And as a bonus, every movement harvests energy, contributing power back to the colony. It's a system that solves one of the biggest hurdles to long-term space colonization, turning a deadly environment into a place where humans can not only survive, but thrive. The future of humanity in space might not be in giant spinning wheels, but in the very clothes we wear. Thank you so much for joining me on this deep dive into future technology. If you enjoyed this exploration of science and space, please hit that like button and be sure to subscribe and turn on notifications so you don't miss our next adventure. Let me know in the comments what other futuristic concepts you'd like to explore. Until next time, stay curious.